So good morning, everybody. This talk was supposed to be given by Udi, but he's not feeling so well, so I was asked to substitute. Had he been here, I'm sure he would have given a better talk, but you have to suffer me. Okay, I was thinking, I was asked to give a review about long-duration GRBs, and this is the first time I hear that this is going to be mostly observational, because it's not going to be, I wasn't told anything about that. So I'll go through a quick review of everything we know, or roughly the important thing we know about gamma ray bursts, long-duration gamma ray bursts. And then I will try to leave some time to focus on the things which are more controversial, that we know less of, that we're less sure of, meaning there is more work to do. Okay, so I guess everybody knows these properties. GRBs were found accidentally in the 60s from these espionage satellites that were trying to look for nuclear explosions in space by the Russians, I guess. Instead, we found these magnificent astrophysical objects. The instrument that collected much of the majority of bursts that we know still today is BATSI, collecting almost 4,000 bursts, so statistical work is coming a lot from that. And today SWIFT is continuing to collect bursts. They are short duration bursts. Even the long ones are short. They last a few seconds, 100 seconds. They over the observable universe, there are a few of them per day. Their spectra is peaked at around an MeV, slightly below, with some spread, but not too large. They're very non-thermal, both in the low energy tail and in the high energy tail. They have high energy tail going to GeVs or more. And they have very short time-scale variability, sometimes going down to milliseconds, more typically some fraction of a second. So this short list of properties immediately led to the understanding that there is a problem. Once you know that the distance to this object is cosmological, it gives you an energy of about 10 to the 51 ergs. We know from different bursts it's somewhat different. It could go to 10 to the 54 ergs or 10 to the 53. With an MeV photons, that gives you around 10 to the 57 photons. If you naively take the variability time, a few milliseconds, and you convert that by multiplying by the speed of light to a size, you get a photon density, and you can calculate the optical depth for photons to leak out of this. And the reaction that they can go is pair creation. Two photons can create electron-positron pairs. These electron-positron pairs that just form can then scatter the rest of the photons, and you'll get a very thermal spectrum in contradiction to the observations. So just this calculation shows you a paradox between the observed spectrum, which is completely non-thermal, and the theory that says that if this is the density of photons, it has to be very optically thick and therefore thermal. And there's basically only one solution that we all agree about. This is the thing that everybody agrees about gamma ray burst, is that relativistic motion solves this paradox. When you assume relativistic motion, I'll come to that in a second, you can get a radius which is larger than the naive estimate of c times delta t by a factor of gamma square. And since the radius comes square into the optical depth, you have 4 powers of gamma reducing that optical depth. In addition, the photons in the source are much softer than the photons that you observe. So if you thought you're observing MeV photons at the source, they are much softer, so they can't easily produce pairs. You need to go very high in the energy tail, high energy tail, to get photons that can create pairs. And that will reduce effectively the optical depth. So it turns out with a Lorentz factor of 100 or several hundred, depending on the burst you're talking about, you can overcome this compactness problem. And GRBs must be relativistic with about this Lorentz factor. There was some discussion what short GRBs are, if they should have the same kind of Lorentz factor or not. It turns out they should have somewhat similar Lorentz factor, maybe a little bit lower is also okay. And I think the record holder for which we have very high energy photons suggests that the Lorentz factor on at least some burst is around 1,000. Okay, this, beside the compactness problem, there are many other confirmations of this relativistic motion. already with the first afterglow, we could say that the motion is relativistic by several arguments, but maybe the most direct one is seeing the scintillation disappearing. So radio objects, they scintillate, and as the fireball expands, it becomes too large on the sky, and therefore it doesn't scintillate. The fluctuations decayed, and that suggested the size of 10 to the 17 centimeters after about a month, which means relativistic motion. In some cases, you can also resolve the source. This is the figure on the right. You can actually see the size of the source, and it agrees again with about the same numbers. When we're talking about resolved sources from the theoretical point of view, sometimes in the future, I hope we can see some images like that. So this is what the image of a spherical GRB should look like, if you could really resolve it. And actually, when we're doing scintillation calculations of gamma ray bursts, we have to take, and I think people don't, we have to take this shape into account. So you see that at high frequencies in the radio, above the self-absorption frequency, you have a very narrow ring, which is pretty dark in the middle. So this is what the theoretical images of GRBs should look like. At low frequencies below the self-absorption, it's more uniform. Okay, so I was asked to talk about long GRBs. There are short and long ones. This is a plot of some of the GRBs, duration, hardness. Hardness is the ratio between photons at some high energy band of BATC to the low one. And you can see that you can sort of see here two groups. Long ones, roughly 10, 20, 30 seconds, but spread between 1 and a few hundred. And short ones, which are somewhat harder, higher in this axis, and around 0.1 second. There is probably some diagonal line that you can put in here to divide between them. So as you go to bursts which you know are hard, they can be even longer somewhat and still belong to the short distribution. This is the original plot that in which the short and the long groups were discovered. If you project that to the T90 axis, the duration of the burst, you can see that there are actually two humps, and the dividing line between them around 1 second is the standard definition of short and long GRBs. In a series of papers with Bromberg, we calculated the interaction of a jet with a surrounding, like you can see in this nice simulation. And we calculated that it takes about 15 seconds for the jet to come out of a star. It depends on the luminosity of the jet, on its opening angle, on how big the star is. Obviously, bigger stars takes longer, not completely linearly with the radius, because the bigger the star is, the less dense it is, and it's easier for the jet to pass through. But it takes about 15 seconds. So we're trying to figure out how to get this distribution of duration, given that it takes 15 seconds for a jet to just come out of the star. So it must mean that the jet itself has to be active for more than 15 seconds, otherwise it will never come out. And it means that we lose all the bursts that are shorter than 15 seconds. So the way to get bursts which are as short as a second or two is to have a burst that instead of a jet that works instead of 15 seconds, works 16 or 17 seconds. So that once you subtract 15 seconds, you have the 1, 2, 3 seconds burst that you're observing here. So the prediction that comes from that, if you have a distribution of duration, whatever distribution of duration, and you cut all the bursts which are shorter than something, and you subtract that same number, the 15 seconds, from the length of all the others that you keep, the immediate prediction is that you get a flat distribution in dn dt, not dn d log t, but dn dt, of the duration distribution. So as soon as we understood that, we went to check, and we seem to be compatible with that understanding. So this is a confirmation. I wouldn't say it's a confirmation of the collapsar model of this jet picture, but it is a confirmation that there is, or a suggestion, that there is a certain time that limits the duration of the burst, and all bursts were probably longer subtracting something out of the real duration. Now it also means, if you look at the distribution of duration above this 15 seconds, you see a very strong power law, so there are only a few bursts which are much longer than that. And that suggests also that the number of bursts which used to be shorter than 50 seconds but disappeared is large. So maybe there are many choked bursts if you take this extrapolation seriously, and maybe we'll make some connection with low luminosity GRBs in a few minutes. Okay, we all know that there are most of the gamma ray bursts come from massive stars. The long gamma ray burst comes from massive stars. There are many evidence for that, starting from this coincidence with some supernovae in 98, with theoretical understanding that collapsars may be able to produce gamma ray burst, with red bumps in many more events, which you can't really see the whole supernova. Position in the galaxies and the type of galaxies they exist suggests that they are well associated with star formation, even more associated with the star formation than the star formation is. And in some cases, you can actually see the supernova spectrum. One of the great clues that we have about the whole mechanism of gamma ray burst is the variability. We see short timescale variability of less than a second, as I said before, sometimes a millisecond or 10 milliseconds, while the burst itself lasts 100 times longer than that. And it's this large ratio between the duration of the burst and the variability that is interesting. So I took here some of the more variable bursts from the BATSI catalog, and I marked the peaks. And you can see that between the peaks, the emission goes all the way to the background level, or almost there, sometimes with big gaps. When you think about the relativistic timescales that are involved, there are two timescales which are equal in this problem. So if you think of something, let's say this shell that came out from an explosion that occurred in the origin here, and at this point it emitted some photon, and then some later time it emitted another photon while it doubled its distance from the origin. So it was initially at R, and now it's at 2R, where it emitted photon B. There is some distance between photon B and where photon A managed to propagate to. This distance is very short because the shell itself moves almost at the speed of light, so they almost catch up with each other. But you can calculate what's the distance between them. It's the difference between the speed of the shell and the speed of light. And therefore, this distance between these two photons will give you some effective duration of the burst, which is about R over gamma square C. And the surprising thing is that this timescale appears in another geometrical thing in here, which is the difference in arrival time between the photon on the line of sight and the photon off the line of sight. Now, you can only go off the line of sight about 1 over gamma in angle. Because of relativistic beaming, the photons that are emitted from here are going mostly in this direction, plus minus 1 over gamma. So this guy just barely makes it to the observer. But a photon that would have been emitted in here, all the photons would go in there and you wouldn't see them. But within the opening angle of 1 over gamma, you can also calculate the delay time between photon emitted at A and at C, and it comes to be about the same thing. So what we call the angular spreading time and just the fly time are about the same. So that means that every signal that you have is being smeared on this time scale. So when you're trying to create this variable temporal profile that I showed you before, if you were trying to do that with a variable surrounding, so you make the surrounding from which the explosion is colliding with, interacting with clumpy, it turns out that these clumps have to be extremely tiny to avoid this angular diameter problem. And when you do them so tiny, the fraction of the explosion that actually hits any of these clumps is tiny, and the whole process becomes inefficient. So the alternative that I think most people now think is the right thing is that the object itself is variable. So you can't blame the variability on the surrounding because you have to make these clumps too small and it's inefficient. The object itself is variable, so that's a huge clue on what the source is doing. It has to be long-lasting, maybe 100 seconds, with a variability of less than a second. And the story now, let's say with the collapsar model, is that you form a black hole, and then you feed the black hole erratically afterwards with some accretion disk that is somewhat unstable, producing all these shells, which then collide internally between them rather than with the external environment. Some people claim that this process is also inefficient because after the shells collide, they're still moving, so they still have some kinetic energy left after the collision. But if you look at that in details, it depends on the ratio of Lorentz factors between shells. So if you assume that the shells have comparable Lorentz factor, yeah, then the efficiency of this process is 10–20%. If you assume that the ratio of Lorentz factor is huge, you can get to 100%. There is no actual limit in here. Okay, let me skip that. I think I said that this is what we think the stages that long GRBs are forming from. Now about spectra. So we think that gamma ray burst form, both the gamma ray burst and the afterglow are produced by synchrotron radiation. If you take a parallel distribution of electrons, presumably accelerated at the relativistic shock, let's say this, to some power minus p, roughly 2, slightly more, and you put it in a magnetic field. You have all these electrons radiating. Each electron has its own spectrum, and when you sum them all up, you get this broken power law, despite the fact that you started from one single power law, because there are some other mechanisms that produces breaks. So one of them is the cooling break. When you go to high enough frequencies, the electrons cool, so even though you injected them in that rate, the actual number of electrons that survive in any given time at high energies is smaller, because those guys cool, so that provides this break. There is a minimum injection energy. So below that, we get the low energy tail of synchrotron radiation. We'll get to that in a second. And at very low frequencies, you have self-absorption. So you have a nu square or nu to the 2.5, depending on the circumstances, spectrum. So you get these 4 broken power law segments out of a single power law distribution of the electrons. Now, supposedly, this should have been the spectrum both in the afterglow and in the gamma ray burst itself. We all know this is the spectrum in the afterglow. We model most afterglows according to this kind of spectra. But if you look at the burst itself, it doesn't seem to fit the spectrum in the gamma ray burst itself. So this is still a puzzle we have to work on. During the afterglow, we can work on how the shocks evolve when they collect more and more material. Basically, conservation of energy, more or less, the fraction of energy that is emitted is limited, both because of cooling that is not completely efficient and because the fraction of energy that is going to the electron is not unity, and you can only radiate that. So if you assume that the energy is constant, or you take some variation of this, the energy is about the mass times c squared times the Lorentz factor square. The reason the Lorentz factor here is square is because you have thermal Lorentz factor of the protons in the fluid and a bulk Lorentz factor of the whole thing, so that's why you get a square. And now if you put some thing for the mass, if the surrounding has constant density, the mass goes like the radius cube. If it's wind, it's only proportional to the mass, to the radius, and if you plug this in here, and you take the relation we just discussed between time, radius, and gamma square, you get all these relations for how the Lorentz factor evolves in time, how the radius evolves in time, and therefore you can calculate all these breaks in the spectrum and see how they evolve. And this gives a description of the afterglow that is roughly, I would say, in agreement with what we observe on long GRBs afterglows. Jets. We believe that the emission coming from GRBs is collimated. Especially it seems to be true for the highly energetic GRBs. This was suspected already just from the energetic point of view because the energy is so large, maybe it's collimated, and also from the fact that we understood that the explosions are relativistic, so we can't see the thing that is not directed to us. So we don't know if it's there or not, so we might as well assume that it's jets. The confirmation came from the fact that we saw the light curve starting decaying faster after a while. And this is because if the fluid expands in its own frame, roughly at the velocity of light, because it's relativistically hot, then when the Lorentz factor of the whole ejecta decelerates below 1 over the opening angle of the jet, you'll have a sideways spreading and a faster decay of the light curves. Numerical simulations of this business have been zigzagging. You can tell us what the latest stuff is. So initially, Andrew used to come and tell me, you know, we have all these theories, but we run it in the simulations, the jet don't really spread. It doesn't work. Then I think some of the theorists also zigzagged. They said, yeah, maybe we can make it not spread. And then Andrew said, oh, but maybe it does spread in the simulation. So, okay. I couldn't know how to make it not spread, so I think this is what it should be, and everybody will catch up, hopefully. Okay. So yeah, this is the steepening I was talking about at some time. And for measuring this time, you can tell what is the opening angle of the jet. A jet break at about a day tells you a Lorentz factor of slightly less than 10. Later, slightly less than 10 at this time, meaning an opening angle of about 0.1 radians of the jet. So the timing of the jet gives you the opening angle, and that reflects on the energetics and on the rate, basically, of these events. When you correct, this is a very old paper, if you correct for the, distribution of seemingly isotropic energies, for the jet, they seem to have obviously smaller energies, but also more concentrated. It doesn't seem as good as this, but still it seems to be okay. The latest time with this, the latest thing with this burst is that with the SWIFT data, we have a somewhat less clear view of these jet breaks. Not always we see them. So I think the picture became more murky in the last few years than it used to be. Shortly, I will mention precursors. I think this is a big clue that haven't been harvested yet. Precursors, they appear in 3% if you define them one way, or 15% of burst. It's some emission that is weaker from the burst itself, well separated from it by background emission. It's somewhat softer, but still non-thermal. So we have to understand what it is. There are several models. One of them is that these are the emission from the fireball itself. As the fireball expands and the original photons of the fireball leak out, you will get a precursor. So I think this is true. There should be this event, but these precursors are not completely thermal, so that doesn't work. On the other hand, where is that thermal precursor that we do expect that should come out of this? So I think we have one precursor that we know should be there that we don't see, and another precursor that we see but we don't understand. Okay, polarization, let me skip that if I'm so much out of time. And let's go back to talk about low luminosity GRBs. This is an exciting thing because it's a new class of objects. And I think they're quite different than the gamma ray bursts themselves. They don't form by this direct jet that we talked about before. So this is a class of GRBs. Some of them are quite long. Some of them are moderately long. They have relatively low energies. This is what defines them, less than 10 to the 50 Hertz. And a spectrum which is somewhat soft. So we think these are some kind of breakout from a relativistic shock. So this is more thermal emission than what we know in gamma ray burst. This is a figure of temperature that you expect from photons coming out of a shock as a function of the velocity of that shock. So initially, you have some equipartition between the radiation density and the matter. It goes like the velocity square for low velocities when the radiation is matter-dominated, so kT is m proton v square. Quite at small velocities, you get radiation becoming important, and then AT to the 4 is equal to v square, and you get a very flat dependence. But then when you get to some fair fraction of the speed of light, the creation of photons behind the shock is not fast enough to create all the photons that are needed in order to arrive to thermal equilibrium. So had you been in thermal equilibrium, you would get these small temperatures. But for velocities which are higher than that, you get way out of equilibrium. And we think some of the explosions relevant to both gamma ray burst and definitely those low luminosity GRBs are of this type. And therefore, you have a breakout with much higher energies than you would naively assume in equipartition. We can talk in more details about how this shock breakout occurs in different environments and how you can calculate everything, but it comes out in the relativistic case from optical depth of order unity. There is a high loading of pairs when the shock is very fast, but then these pairs annihilate and the radiation leaks out. The temperature in the local frame is set to be something like 50 keV, because this is the temperature where most of the pairs annihilate. So regardless of the conditions exactly of the shock, the local temperature is 50 keV. The observed temperature will be 50 keV times gamma. So if you take that simple theory, you have basically two parameters, the Lorentz factor of the shock and the radius of the shock. And you have three observables. The temperature of the photons that you see, which I already told you, is 50 keV times gamma. The duration of the event, the same R over gamma square. And the energy of the photons that leaked, it's not exactly the initial energy because it was degraded by some adiabatic expansion and you lost some, but there is some expression. So you have three observables and only two variables in this theory. So the theory is over-constrained, and you can check if those three observables satisfy this relation. Okay? So if the duration of the burst is proportional to the energy to the 1/2 power and to the duration to the -3 power. And since the temperature, the observed temperature to the -3 power. So if we go to the list of bursts that I showed you before, it seems to be roughly satisfied with a Lorentz factor of between 1 and 3 for these low luminosity GRBs. So it's interesting to know if in the distribution of bursts that we have, and we all think of them as long GRBs, how many more classes like these are there? This seems to be a well-defined class. In the real space event, in density of events per unit volume, they seem to be the majority of the events, even more frequent than GRBs, but in the observed ones, they're pretty rare. Let me skip that, and I'll say that only in the summary. So this is a list of the thing I more or less talked about, and I ordered them here in the order of what are we sure of in the long GRB business, and what are we less sure of, we know less about. We don't understand the spectrum, the fact that the spectrum is not thermal. This used to be called the line of death. Maybe I'll put a slide on this. This is a compilation of the sharpness of spectral peaks in GRBs. And instead of measuring the low frequency tail, which is so far from the peak that it's hard to analyze, what was measured here is the width of the peak, or some measurement of the angle subtended by the peak. And you can see that if you compare that to synchrotron emission, even from a very well-concentrated set of electrons, not even distributed as a power law, most of the bursts have spectral features which are wider than that. So I think this problem with the synchrotron radiation for the prompt gamma ray burst itself is real, and it's more severe than we thought of before. It's almost in all bursts. Low luminosity, I think we more or less understand. Reverse shocks, we see them every now and then, maybe not as frequently as I would have expected. Afterglow is well understood. Jets, somewhat well, not as well. And I'll end up here.
So some long GRBs turn out to be rather smooth or somewhere in between. The standard model of internal shocks kind of gives you some potential for creating this variety, but do you think that it's natural to get such a wide variety in the standard model?
You know, I don't really understand this complexity. So the fact that you're saying that there is an internal shock model doesn't mean that the burst should be very complex, because it doesn't tell you how many, you leave it all to the accretion disk that feeds the black hole that was just formed to create all this for you. So I wouldn't know. If you ask me before I would see in the data, would I expect 100 peaks? I wouldn't. Would I expect just a single one? Maybe. So I would say there is a chance for a variety, but I don't know. Now, for example, for the low luminosity GRBs like 98BW or things like that, they are smooth. But we think they are formed in a different way. So some are definitely formed in a different way, and some could be just internal shocks with fewer shells, and therefore smoother. The internal shock in that sense is very unpredictable. So
you mentioned that the precursors, you would expect them to be thermal from a fireball.
Yes,
could you explain that? What fireball, and why is it emitting gamma rays?
If you take a collection, you take some energy and some pairs and some baryons. You put them in a localized small region. You let the whole thing expand. Eventually, the fireball will become optically thin. As it expands, it will eventually become optically thin. When that happens, the photons that are there, they leak out.
So why does this happen a few minutes before the explosion?
Okay, so presumably, if the internal shocks are doing the, or even the afterglow, the emission, the main emission that you see, that happens when the things interact either with itself or with the surrounding, and the photons that are coming from the fireball, they leak before that. And they have to do that before, because if you want the gamma ray burst spectra itself to be non-thermal, it has to happen when the fireball is optically thin. That was the whole idea in going to this multi-stage model here. To start with a compact source, but there it's optically thick, and you do the internal and external shocks when it's all optically thin, so you can get non-thermal spectrum. So somewhere between those, there's the transition between thick and thin, and it happens before stage 3 and 4. So that's why you expect the precursor to be before. Now, some people were claiming that, well, okay, forget this. Yes, next second.
But at the same time, you made the point that the spectrum does not seem to be fit by a power law population of electrons for the gamma ray burst itself.
Right.
So could we just witness the transition region? I mean, maybe the gamma ray burst itself is the transition between the two regimes.
Yes, this is called photospheric emission models, and yeah, I think it may have some merits, I don't really know. Yeah, I was making the point that just synchrotron is not going to work. You have to add either self-absorption, which doesn't seem to work because the thing is too big for self-absorption to be important, too big and too hot, or some scattering. So yeah, we can observe bursts in some transitions.
Okay, just a quick comment. When you made your sky map of what an afterglow looks like on the sky, that calculation assumed that you were on axis, right? So
yeah, that was spherical.
Right.
So
no,
on axis.
But the viewer was on axis. Oh, that was spherical, okay. But if it's a jet and you're off axis, that should look more like a crescent, right?
It will evolve as a function of time. So at early times, it will look just like this. And at late time, it will look similar to this. And in the middle, it will be a crescent. Right? So at early times, you don't know that it's a jet because you see a small region out of the jet, so it's like a sphere.
Yeah. Okay, good.
At late times, the jets spread out. So even if you were off axis, you are effectively on axis at very late times. So it will be like this again, and in the middle it will be a crescent. And this is also the place where we expect polarization, which I haven't had time to talk about.